My name is Aaron Shalakis, and my colleagues Bailey, Davi, Tarun, and I are here to discuss biologically reliable integration and design of ground environments in space. That's a mouthful, so we have our fancy acronym BRIDGES. And essentially, we are trying to look at how do we get a greenhouse into a planetary surface in a way that's going to provide reliable environmental control and life support systems. Next slide, please. There we go. I'm not sure if we have lag, but anyway, in order to get from A to Z, we should probably begin with A. So I'm going to take a look at the existing physicochemical ECLSS architecture on the International Space Station. I'm also going to introduce a very special guest. After that, I'm going to hand it over to Bailey, and she's going to talk more about the tools we're going to use to bridge from the existing architecture to future architectures that involve biological life. Speaking of, our friend Davi will go into some of the details we need to look at of the biological life, and then Tarun will come clean up with how we plan to execute this vision in the beginning. Next slide, please. So what exactly is ECLSS? Why do astronauts need it? As we all know, as you put crews into space, the environment there requires various countermeasures to allow them to survive and thrive. I'm not going to go over all the bullet points in most of my slides. A lot of this is already known, but as you can see, I've kind of separated the gaseous inputs and outputs from the more liquid and solid inputs and outputs, because that's the scope of work that we are going to look at in this phase of our project. Next slide, please. So here's a very simple overview of the existing environmental control and life support systems on the space station. So there's 5 subsystems noted here. And again, we are only going to be looking at the gaseous aspect of things for the scope of our discussion today. So the left 3 subsystems are what we're going to hone in on here in a moment. Next slide, please. Okay, so again, we're looking to put this greenhouse on the surface of the moon or Mars. So we have to ask ourselves, what are the concept of operations for that? So on the left-hand side, we have choices that can be made, and essentially all of the left-hand side choices are what we're going to be looking at, because that's going to give us the most bang for our buck, if you will. So we're looking at expedition level durations, where overhead mass is actually more valuable over time because it provides more functionality, especially as your gases, liquids, and solids all become more recyclable as opposed to consumable. So again, we're trying to bridge the gap between existing physicochemical technologies for ECLSS and push into the biological side of things. Next slide. Excuse me, next slide, please. So here's our special crew member, our buddy Bridges. And just like the crew, biological life will have inputs and also requires environmental control. And of course, we'll have outputs. Next slide, please. So again, focusing on the gaseous state more than the liquids and solids, but we have similar impacts to the physical chemical systems, and we're going to break that down further and look at each of the impacts to each of the subsystems. So next slide, please. And that all basically boils down to one of the functions of this atmospheric control and supply, which is atmospheric monitoring. We're going to have a lot of dynamics that are changing with O2, CO2, water vapor, and that's going to impact all the other subsystems downstream. So this is the logical beginning or place to start. Next slide, please. So this slide and the next slide basically break down each of the individual impacts to each function of these three subsystems. Again, I'm not going to go over every single one of these because the next slide actually has a summary of them. But I will note on the left-hand side, the trace contaminant control and monitoring is a rather complex topic. Again, just to bound the existing project, that will be out of our scope, but that is a logical next step that we could take. But for now, we are focused more on the major constituents that take up most of the volume of the atmosphere. On the right side, if you notice under the ACS system, I've highlighted psychrometric complexity will be increasing significantly. And you can see that monitoring locations and increased precision is a theme that is occurring across the board here. Next slide, please. Oh, there we go. Okay. And so our third subsystem on the left here, again, we have increased complexity of both the psychrometric algorithm and the major constituents. So that's all reflected in the right side of the slide. Again, we need more monitoring locations with more precision to help characterize these increasingly complex algorithms by introducing biological life in phases. So how are we actually going to manage this challenge? Well, now I'm going to hand it over to Bailey. She's going to discuss some of the tools we're looking at to do that.
Next slide, please, Drew. Hi, everyone. As mentioned, my name is Bailey. I'm excited to talk to you guys about how exactly we are planning on doing this. So essentially, we are planning on implementing this with starting on Earth and taking it to space. And that's the way we see this going, where we're going to have our bridge design implemented into analog environments. I'm sure you guys are familiar with Hera, High Seas, MBRS, all those fun places, Lunaris, and we want to eventually go to Antarctica as well to start making sure this works in an analog Earth and gravity. And then we want to take it to space and start looking at ISS. Obviously, we have ECLSS, environmental life control systems on the ISS, and this will help us monitor what's going on there. And then eventually, we would like to see this go on to the lunar and Martian surface. That would be very exciting, to where we can accurately predict what's going on there. Next slide, please. And this is a quick list of all the complex things that goes into what we're trying to do here. So essentially, the monitoring of it, the input of other systems, just within biological systems, we're all aware how complex we are as humans or plants. These are all the other things we need to think about: power, thermal control, the crew and plants, how we get that information to move. And that is why we are saying that we really need a good systems engineer to be working on this. And that leads us to the tools we will be using to implement this. Next slide, please. And we will be using something called model-based systems engineering. This is MBSE. This actually has a software background that's being implemented into a lot of different industries, including the aerospace. It was introduced in 2007 by COSI. And it uses a system language to do so. And the really exciting thing is that it actually was used on NASA's Pathfinder. So there is kind of some legacy here in aerospace that you can use it for aerospace. It's something that a lot of us believe we should be using in aerospace. And this is a great opportunity for us to show that it can be used. And essentially, the quick definition of it is formalized application of modeling. That's what, Wikipedia defines MBSE as. And basically what that means is there's relationship clarity. So it's really easy to see all those systems that I listed and everything, trying to figure out what's going on there. It's going to help us define what's going on there, and the inputs and outputs, and then also define what the system function is of what should be doing what, when, basically. The three main areas of MBSE where we're going to be focusing is the system architecture of designing bridges, the system requirement traceability, so all the different things you have to think about when it comes to keeping things alive in space. There's requirements there. We're going to make sure that they are all talking to each other. And then finally, the system and organizational process flow. So that is MBSE in a nutshell. To next slide, please. And this is, one back, please. Spoiler, sorry, guys. There we go. So as I mentioned, we do need a strong systems engineering plan, and we're planning on implementing MBSE from the beginning in the concept phase through design development and eventually into operations. So this is especially important because it is an iterative process. As kind of mentioned, our goal is to have a single organism, wheat, for example, and then eventually scale it up to where we can help the monitoring defined in from like the single plant up to what are humans doing to what is a habitat doing with the plants and the humans acting together and other organisms, possibly algae or other, even animals possibly, and then eventually into an entire, civilization. And our goal is to be able to have someone be able to input what they have. I have 4 humans and 3 wheat plants and this much algae and exactly like that. And we can work from there. As you can imagine, that's very complex. So that's where this iterative process comes in, where we can define one thing and then grow from there and show the relationships. And it's going to be done in this very scalable, modular effort with very, very clear inputs and outputs. And an example of MBSE that I was able to find in space actually is over here. This is a use case diagram. And a big part of MBSE is you're going to visually be able to see what is acting on what systems and what functions. We're going to have flow diagrams, use case diagrams, and it's going to start with a single week and then flow outwards into all the different things that you're going to need in space. Speaking of all those different things you're going to need in space, I'm going to hand that over to Davi to talk to you guys about.
Hi, everyone. Thank you, Tarun, for passing these slides. Well, we need to start in a way, in a point. And for that, for now, we are dealing with the biological life. And for now, we are focusing on the plant. And with that, the plant will be allowing us to have some parameters and requirements that will be useful to us to start really deploying our system, our proposal. And this also starts with the plant selection criteria. For that, we have selected the wheat as our first type crop that we'll be dealing with on bridges. And this criteria, as I can mention here, of selection of for the selection of wheat is related to some studies that has been conducted not only in terrestrial, but also in space analog environments. And some of these studies, it has started with the studies of Monge and Bugby in 1998 in controlled environmental chambers, which has allowed the study of wheat, of how the CO2 enrichment affects on the wheat respiration. And then some studies that has been conducted by Dr. Wheeler at NASA, especially with the biomass production chamber, the BPS. This has started in 2002. This system was ascended on the shuttle, space shuttle, and also at the ISS, as you can see in the left top picture. And this was the first precise environmental control, the first system with precise environmental control, which allowed the atmospheric control and has provided some insights related to the atmosphere and also the plant canopy and photosynthesis and how the wheat will be growing in these situations, in these imposed situations. Then the most recent studies has been conducted at the ISS, starting with the advanced plant habitat, which was deployed in 2017, and the advanced plant habitat, also well known the APH, it's the first artificial environment designated to cultivate crops at the ISS, was the first system designated to that. It's an artificial and closed system provided with a lot of cameras and also more than 180 sensors, allowing studies on field phenotyping of wheat and other crops. And other criteria that we have highlighted here for our for the plant selection is related to social-cultural features. The wheat is a crop that allows us to have many type of meals that are really common to us in our daily lives. And it's possible to provide pasta, noodles, bread, pizza, chapati, and many other type of meals, allowing this the social-cultural, because in space there will be astronauts from different countries and different cultures. And the final one and the most important one is the nutritional content. When we are dealing with the sustainable human presence in space, the nutritional content of the crops, of the crops that will be cultivated in the greenhouse will be the most important factor, because this will be providing the necessary amount of nutrients for the human diet. And the wheat is a high dense calorie crop, and it's provide approximately 1/5 of the calories and proteins that are necessary to the human diet. And next slide, please, Arun. And then we were able to take a better look in this table. This was presented last year by CAISTATS during the Mars Society Convention. And this was kind of highlight by Dr. Wheeler of different type of crops that has been conducted in some space agriculture studies. And all of these studies has provided many data about this type of crops, about the period of the growth, how much grams was cultivated by hour, and also the biomass, not only the edible, but also the non-edible biomass. And the most important parameters that we'll be dealing with, as was well said by Aaron, for now, we are looking at the gas features in the atmosphere. So the wheat, we are considering here in our approach, not only the edible biomass, but also how much O2 has been produced by the crop that was delivered for will be delivered for the environment, but also the CO2 removal. Next slide, please, Arun. Well, and considering the subsystems that will be aboard the bridges, for the analysis and integration of these, we need to start with the system and it goes, the definition of the system and it goes. So this will be providing us a way to understand better and have some conclusions on the operability, the productivity, and the most important indicators that we have now that we are considering for the bridge is the reliability for this system. And to provide that, we considered a hybrid approach dealing with not only the technological inputs of the physical chemical parameters inside the environment, but also we'll be integrating with the mechanical side of a life support system. And as you can see in the picture, we are dealing with a more complex system. We started with the idea of a life support system, and then we are expanding what we for now know about environmental control life support system. This will be providing us an approach to really bridge this gap to a controlled environment, a controlled ecological life support system, and integrating both of these features, not only consider the environmental control side and the technology that will be aboard the environment, but also we will be dealing with the ecological life, the ecological system that will be there. And bridging that, we'll be able to provide future inputs and also supporting some research that will be providing an effective bioregenerative life support system for future space settlements. And some technological assistance that we are considering for the greenhouse environment will be the monitoring sensors, data acquisition systems, automation and control systems supported by microcontrollers, and also the most important one for our current approach will be the smart management of air ventilation inside of the bridge. Next slide, please, Arun. And with that, considering the modularity and the scalability that was mentioned by Bailey, for now, we are not, will be able with this approach, will not be able to start to continue with only wheat. We'll be also able to provide other inputs, other resources like seeds, water, and nutrients, and other different type of crops, but also humans. Putting that in this ecological environment, we can have not only different type of crops, but we can start with one human being or astronaut, and we can increase that to a four astronaut crew, and even like integrating a higher amount of astronauts for a space settlement. And this will be interacting, the plants will be interacting with the humans, and this will be supporting how we'll be dealing with the environmental control, and will be also giving us some outputs such as the edible biomass and the atmospheric parameters like the CO2, the oxygen, and also the water vapor abroad the atmosphere. Next slide, please, Tarun. And considering the environmental control, how much complexity we are dealing with, the environmental control has been considered a major engineering challenge in research conducted in space agriculture, and also with plant production. And this, for that, based on that, the environmental control, the best environmental control system will be not only that provide the adequate environment for the plants, but also that can do the control of that environment in a way that doesn't affect how the biological life and how the architecture will be interacting with each other. And as you can see in this pyramid,
5 minutes.
Okay. And as you can see in this pyramid, we have the biological in the bottom of the pyramid, the biological and the architectural environment, the plants and the technological aspects integrated with an ecosystem that will be providing, that will be allowing us to better understand the atmosphere, and this will be manipulated by the environmental control. Next slide, Tarun. And now I pass to Tarun to conclude our presentation.
Thank you, Davi, and powering through. So how exactly do we get from what my colleagues have spoken about to what we want to see? It's really not going to take long, because what we're doing over here is we are leveraging the existing technologies that are already out there. The experiments have been done, the research has been done, and all these technologies are existing, and newer technologies have come out. And we will be using that newer technologies like model-based systems engineering model, and integrating that with our research. And that will give us an estimate of exactly what is the permutation and combination of different technologies that we will be needing to bridge that gap between ECLSS and cells. And this process is also giving us an idea about exactly where the loopholes are within the systems and how exactly do we fix them, as well as improving upon the existing models that are available with the newer technologies that we have. The best thing about this is that we get to test it as well. And so for testing and for doing all this, we kind of need money. So what exactly is happening in that particular scenario? In the past, when the space shuttle was carrying up all the water and all the resources required by the astronauts to International Space Station, per kilogram estimates was about 54,500 for the space shuttle. And for Falcon 9 currently, it's about $2,720 per kilogram. And imagine that the costs of launch have gone down significantly, but most of this costs are also you're paying per kilogram. So if the weight goes down, you get to save more money, because currently per launch, SpaceX is spending about $62 million. And bridges, this concept will essentially drive that weight requirement down. So we can essentially save a lot more money in the future, because we don't have to send as many resupply missions as is required at this current point of time. as we mentioned, testing. In the past, most of these testings have been done in analog stations, and one of the best examples is the test that was done way back in the mid 90s at the Amundsen Scott South Pole station, called the CELS Analog Research Station project. And they experimented with all the different systems that is required for a closed ecological life support systems, and have a lot of research published through NASA Ames and through other places. And
1 minute.
This integration is absolutely essential, because most of the other analog stations that we have over here have a lot of problems with integrating all these new systems that is required because of the power requirements and because of the space requirements, etc. Now, moving on to actual space environment, we've had different things done already, as Davi discussed, in the advanced plant habitat and the veggie systems. And in the future, we would be testing that over here as well. So in conclusion, why do we have to choose bridges? Bridges is one piece of technology that we have that can be used as a test bed for all these integration of technologies for the long duration missions. And this is a key element that will help us progress towards the closed loop systems that is absolutely essential. So we can have a complete remodeling of Earth's ecosystem or bioregenerative life support systems on Mars. So we don't depend on Earth's resources when we go there. Thank you. We're open to questions now.
Okay, unfortunately, that's all the time we have. I will say, though, that the next session is beginning. So thank you for the presentation. It was very interesting. If there's anybody that would like to stay behind and have some questions, there is some overlap, but the next sessions are beginning now. So I know that Aaron was answering a couple of questions in chat, but if anybody else has any questions, feel free to stay, but the next sessions are beginning now.
Thank you.
Still got a bunch of folks here. Anyone got questions?
Have you done any actual hardware testing yet, or is this mostly just research into the design concept?
Currently, this is just a design concept at this point of time, but we plan on testing it at different analogs going forward. And one of the analogs is located in North Dakota. This is where I work at this point of time. And we will be testing it up at different analog stations across the world to get the things moving forward as and when we have the opportunity to do so.
So who's building all of the hardware? Is that being done on site, or?
Bailey, do you want to take that question?
Yeah, we'll be working with probably Tarun's group and figuring out how to actually get everything integrated together. So we don't have a single place right now, but we're hoping it's going to be tied to some research.
Ah, gotcha.
Any other questions?
For anybody that's sticking around?
Like the room's thinned out quite a bit.
Yeah, the new, like I said, the next track sessions are beginning. Well, thank you for your time. I wish we had more time for questions, because I think it's an interesting concept and it's going to be critical for any future expansion. But I'm going to go ahead and let everybody go so they can get to the next sessions.
Yeah, thank you all so much. Sorry for the late start. Next time we'll have time for questions.
Thank you very much.
No worries. 30 minutes is a rough time. Rough
Bye,
time
everyone.
slot. So have a good day.